Okay. So we will start with the Black-Scholes merchant model quickly and then move on from there and show you some applications of that. But before I do that, any questions from yesterday? Anybody has any questions from the binomial tree bit yesterday? Okay. It seems nobody has any questions, so I can start. I can continue. Now, what we did yesterday was pricing the options, and in effect, remember, we will see that as well, that the only way to price American options is by using the binomial tree approach. The European option, on the other hand, can also be priced using Black-Scholes and Black-Scholes merchant model. Why is it called Black-Scholes and merchant model? Because the same model or the same solution was arrived at by Black and Scholes and which is the Black-Scholes paper that came out in the Journal of Political Economy, and the other was this paper by Robert Merton, which came out, I think, in the Rand Journal, which also looked at the same thing. And then both of them did it independently. So while in the short term, the hello. Hello.
Yes, we can still good. We
Hello.
can hear you.
Hello. 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 I'm back. I don't know what happened. Yeah, okay, you can still hear me. Good. Because I can't see the name flashing, so I couldn't figure out. Okay. So both of them kind of did the same work around the same time, and therefore, subsequently, when in 1997 they got the Nobel Prize, Fisher Black had passed away, so he didn't get the Nobel Prize, but he was mentioned. And these two people, Myron Scholes and Robert Merton, got the Nobel Prize in 1997 for this work. Now, the idea of this. So okay, again today this plays up. So it assumes, so what, okay, this is the basic assumption that the market works on. And the assumption is what is called as the log normal property of the stock price. Again, today this is not showing up properly, but in your slide, I'm sure you have the full data out there. So what you can see, I mean, effectively what you see is the last line, that the logarithm of ST is normal. In other words, the logarithm of ST is distributed normally with a certain mean and a certain variance. So the mean and the variance is computed out there, and you have the logarithm of ST that you can get. Now, why am I talking about the logarithm of ST? And why not ST? Actually, I want ST. And therefore, as you can see, the last part of the sentence, I say ST is log normally distributed. But why don't I assume normality on ST? The reason I do not assume normality on ST is because of the simple thing that if ST is normal, remember the range of the normal distribution is from minus infinity to plus infinity, which means that with a positive probability, you will end up getting a negative value. Your outcome may be, your value can be negative, but that will happen with the positive probability. Now, in general, if you just have a normal distribution, if the underlying value becomes negative, that is not a challenge. But the problem here is that the underlying value is price. The underlying value here is price. And how can price be negative? Price cannot be negative. So therefore, you cannot have a logic of price being negative. Hence, you cannot assume normality of the underlying asset price. However, having said that, well, while asset price cannot be negative, the change in asset price, that is, how much is the change in the price from today to tomorrow, or from yesterday to today, that what is also referred to as a return. The return can be both positive or negative. The change in asset price can be both positive or negative. And therefore, one can assume normality on the return. Now, assuming normality on the spot price is a problem, because that would mean that you are assuming with positive probability the spot can become negative. Obviously, that does not make sense. But on the other side, return becoming negative is not a challenge. Return can become negative. Right? Return can become negative, and therefore the return becoming negative is not really a challenge per se. So we can assume, and then obviously return can also be positive. So we assume normality on the return. Why do we take return? Because remember, realize what I want, what I know is the current price. What I want is the future price ST. So therefore, if you want to look at it, ST can be written down, the future value can be written down as today's value plus the change in values over the entire period. Right? And let's say it's a daily change, so the daily change in values over the entire period. The sum of all the changes and added to the current value will essentially give you the future value. So therefore, the need to look at the non-overlapping returns per se. So that is why we look at the return, and the return distribution is can be easily assumed to be normal. Now, if you assume the return distribution to be normal and then you do a little bit of algebra, you will end up getting to this point where the asset value will actually be log normally distributed. The advantage is that while the minimum of the log of the asset value is negative minus infinity, remember, therefore, the minimum of ST will only be 0. Now that makes sense, because after all, what you are saying is the minimum asset price is 0. The minimum asset price, the minimum value of the stock price can go to 0. That is not a, and the lowest value it can take is going to be 0. So that is not a challenge. But it becoming negative is a challenge, and that is what this kind of does. This process allows me to do. Now, what is this? This is a simple example. What am I doing? I'm saying let's the initial price of $40, expected return of 16% per year, and a volatility of 20% per year. What is the probability distribution of the stock price? Simply go and plug it in. Your price is 40 plus your return is 16% per year. So therefore, it is like 16% into per year, and then that 16% of 40 in 6 months, plus your volatility is 20% of 40 and in 6 months, and therefore you kind of you're given the outcome that you can see in the slide. So therefore, what do we get? We get the mean and variance for the standard normal distribution. We also know that 95% of the time the normal distribution value will be between 1.96 standard deviations. The mean has worked out to be 3.759. Remember, log of ST is what you need to take. So log of 40 and all of that. So that is, just plug it in the formula, you get that number. So what we know is that this log of ST has with 95% confidence is between those two limits. If that is log of ST. We are not really worried about log of ST. What we want to find out is the value is what should the confidence interval for ST. And how do I get from log of ST to ST? Just take exponential. E to the power of log of ST is ST. So therefore, if I take e to the power of the function on both sides, I will get that function, and hence I get 32.55 less than ST less than 56.56, and that is how I kind of get this number, get these expressions. Right? So therefore, what we get is that there is a 95% probability that the stock price in 6 months' time will lie between 32.55 and 56.56. So what we therefore know is that if I go back and if I say if the current value of the stock price is 40 and this is the expected return and the volatility of the return, where will it go in 6 months' time? What is the range in which it will go? This is what I kind of land up having, that I get in this range, 32.55 and 56.56. Okay. Now, the Black-Scholes model can be kind of easily solved by looking at this. What do we know? We have to find out the option price and we have the underlying asset price. Realize the uncertainty or the volatility, this randomness that comes in is in both cases is based on the same underlying. And the underlying is the stock price that we're talking about. And therefore, both are exposed to the same source of uncertainty. Whatever uncertainty impacts the spot price is what impacts the option price. Why? Because after all, the option price is dependent on the spot price only. The spot price. And if there is an uncertainty in the spot price, that uncertainty gets translated to the option price also. So both of them have the same source of underlying uncertainty. We can thus form a portfolio of the stock and the option in such a manner that this kind of takes care or eliminates the entire source of uncertainty. Actually, not the source of uncertainty, but the entire impact of uncertainty. So what we can do is we can kind of write it down in such a manner that it will eliminate the source of uncertainty. Now, such a portfolio like that, such a portfolio, is therefore instantaneously riskless. So in a very short period of time, it becomes a riskless portfolio. For a very short period of time, it becomes a riskless portfolio and therefore can only earn the riskless interest rate. Right? So that is what we do. And this argument is what subsequently goes on to and leads you to the Black-Scholes-Merton differential equation. So the next thing is we'll talk about the Black-Scholes-Merton differential equation, and then subsequently, once you solve the Black-Scholes-Merton differential equation, you will end up getting the solution to the Black-Scholes framework. I hope it shows up. Yes. Okay. Now the Black-Scholes framework has these 7 assumptions. So the Black-Scholes world is based on these 7 assumptions that we can see out there. What are they? The first one is that the Black-Scholes model follows an equation of that order. It is called a Neto process or a geometric Brownian motion, where mu and sigma are constants. Mu, and I'll explain what that is, and the equation is of that order. Now let us explain what this equation is before I go forward. What is ds? ds is nothing but the change in the value of s. So I'm sorry, that should actually be capital S and not small s. So d capital S is nothing but the change in the value of the spot price. So change in the value of the spot price. This is dependent on mu is the drift rate or a con. So you're not talking about daily changes or something, but if you look at over a longer period horizon, if you look over a longer period of time, what is the change in S? And that is what is given by not change, I'm sorry. What is the direction in which the spot changes, the spot moves? And that is what, so on the whole, does the price rise, does the price go down? And if the price remains constant, then obviously ds will become, your mu will become 0. So what is the price? What is the overall directional move of the underlying asset price? That is what is defined by the drift or mu. What is sigma? Sigma is the volatility. In other words, what is it? It is the amount of change that can happen in the asset price over a certain period of time. Now, so this is the volatility of sigma. Now, why am I multiplying by S? There are 2 reasons of this. The mathematical equivalent is if you divide both sides by S. If you end up dividing both sides by S, what you will end up having is that ds over s will be mu dt plus sigma dz, right? So I'll have to explain what dz also is, but if you do that, what you will end up having is the you'll have dz over ds over s. You'll have ds over s, and then you'll have mu s mu dt plus sigma dz, because all I've done is I've divided both sides by s. Now, if it is ds over s, and then I'm not really interested in ds and all of that. What am I interested in? I'm interested in the future value st. So what do? I integrate. I integrate between 0 to t. So integration of ds over s between 0 to t leads me to log of st minus log of s naught. Log of, because ds over s, integration of that is log of s, and therefore now it is between st and t and 0. So I get log of st minus log of s0. But the initial value s0, or the log of, and therefore the log of s0 is known to me. So therefore log of st is basically nothing but log of s0 plus whatever other term. So what do I get? I've got log of st. And now I know from log of st I can easily get to st by taking the exponential. So log of st is now, so I can essentially get to my st term, and that is where my advantage lies. Now what about the right hand side? So as I said, mu and sigma are the drift rate and the rate of volatility, and the volatility rate, right? Why am I two additional things? Why am I multiplying it by s on the right hand side as I have it? And what is dz? Okay, let's answer the first question. Why am I multiplying by s? So let's assume that your price of an asset is $100 today. The current market price is $100. I tell you that your return is constant at $10. So if your price is 100 and you're earning $10, your return as a percentage is going to be 10%. But I have kept your $10 of income as constant. Now, if that is the case, when the price goes to $200, the value of the asset, the return becomes 5%, because the return is is 10 and on the price of 200. Therefore, the price becomes the return becomes 5%. And if the price falls to $50 from the $100, your return becomes 20%, because it's 10 over 50, therefore it's 20%, right? Now this does not make sense, because normally when the price goes up, your return should be going up, and when the price goes down, your return should be going down. But what is happening with the constant return process is that if the price goes up, your return as a percentage goes down, and if the price goes down, your return as a percentage goes up. Now this does not make sense. So therefore, instead of taking return to be constant, let us take the rate of return to be constant. And then I get the thing that as the rate of return is constant at 10%. So when the price is 100, you earn 10. When the price is 200, you earn 20. When the price is 50, you earn 5. And therefore, at least we are talking in that broad framework, which kind of works. So that is what we have done. The next thing, the second thing that you need to do, that's what I've done. Now that is why I'm keeping S on the other side. What is S? S is the current price. So the amount the asset price can drift by, or the volatility of the asset, is going to be a function of the value of S. So S essentially defines the amount to which it can move by, or from where it can move by. Also, what is dz? Dz is what is called as the Brownian motion, as I've written out there, or a Wiener process. Dz is actually mathematically written down as epsilon square root of dt, where epsilon is a normal distribution with 0 mean and variance 1. So let me explain this in this manner. Think of a regression equation. Right. I don't think I have it here. No, I don't have it here. Okay. Think of a regression equation of the what are the terms, what are the coefficients of a regression equation? So if I ask you to regress y on x, what will be the equation? What will be the regression equation if I ask you to regress y on x? So if so, this is the okay. If I ask you to regress y on x, this is the equation that you one form of the equation that you will get. Right? And if this is the case, then I can have four possibilities. Right? Agreed? Right? These are the possibilities. Now look at it. When in this case, this would imply, if we take this would imply the price is always negative. How can price be negative? So therefore, this cannot come in. If you take these two, well, you will get parts where price is positive and parts where price is negative. So that should not make sense either. The only one that can kind of make sense is this one, right? This is the only one which can kind of make sense. But there also I have a problem. You see, if A is positive and B is positive, let's say X is time and Y is price, then if both are positive, can time be negative? Can time be negative? What do you think? Can time be negative? Guys, can time be negative? Can you have negative time? Guys, can we have negative time? What do you think? Can we have negative time? Can the value of time be negative? Guys, what do you think? Quickly. Can time be negative? Can time be negative? Guys, can time be negative? Somebody, can time be negative? Guys, please wake up. Can time be negative? Can time be negative? Can you have negative time? No, right? So please answer. Why are you all waiting so long to answer? I've been asking you for the last 2-3 minutes. Time cannot be negative. If time cannot be negative and your A and B are both positive, then you see price can only keep on increasing. But it does not make sense for price to only keep on increasing, because in reality, price can be going up or price can be going down also. So you can have a drop in price as well. Price should not only be an increasing function. And if price should not be an increasing function, then obviously only positive numbers will not help. So that is where the dz term comes in. Dz, as I said, is basically epsilon, let's say E, epsilon square root of delta t. Now delta t is time, and therefore the square root of delta t is also taken to be positive. The epsilon is a drawing from an n01 distribution, a random drawing from an n01 distribution, and that is obviously that can be both positive or negative. So depending on whether epsilon is positive or negative, the dz term becomes positive or negative, and hence the second term becomes, remember, sigma is volatility, S is the current asset price. These cannot be negative. So if sigma S is positive, then only when this term can be negative is if you multiply it by the negative term, which is dz, because of the epsilon term. Not always, but occasionally. And that is what will cause the price to change direction. Now, so that is the equation that that equation is what is referred to as the Black-Scholes differential equation. Black and Scholes differential equation. Specifically, that is referred to as the Black and Scholes price differential equation. Some of the other assumptions that go in are these. You can read that short selling of securities is permitted with the entire amount being used, so there is no tax, basically no transaction cost. As I said in the next one, there are no transaction costs. All securities are perfectly divisible. In other words, every security can be divided into as small a unit or as large a unit as you want. There are no dividends during the life of the derivative that we kind of take. We can adjust that later, but we will not take at this point. There are no riskless arbitrage opportunities, so there is no arbitrage possibility. We make an assumption that the securities trading is continuous, though practically speaking, securities trading is not continuous, because you have it ends at, let's say, 5 o'clock for the day and only opens at 9 o'clock tomorrow morning. But we assume it's continuous. In other words, we assume that the 9 o'clock to 5 o'clock today to 9 o'clock tomorrow morning is not there. So where it closes at 5 o'clock today is where it opens at 9 o'clock tomorrow. And the other assumption that we make is the interest rate is constant and the same for all maturities. Now, there are two assumptions, the first and the last, which are a little controversial. One of that is an assumption of constant sigma. Why should the volatility be constant? So as we were talking about yesterday, the volatility should not, it is easy for us to use constant volatility because that kind of helps us in that process. But it is not necessary for the volatility to be constant. But yes, here we assume that volatility is constant. The second bit is this interest rate being constant and the same for all maturity. Now, this may not be actually true any longer, because today, if you, for example, borrow for 1 month, and if you borrow for 6 months, and if you borrow for 1 year, the interest rates are not going to be the same. The interest rates are going to be different. When they wrote the paper, when the papers were written and then the model was developed, the argument of this differential interest rate for different periods was not there, and therefore the assumption was that it is kind of the same for all periods. And he assumed that the risk-free rate of interest is R. So now the question is, why risk-free? You could take a risky interest rate also, but when you take a risky interest rate, the riskiness is different for different people, and hence the value of R the risk premium will become different. So to avoid that confusion, we just take the risk-free interest rate to be R. Now I'm going to skip this bit. You can skip these slides. I'll tell you these 2 or 3 slides you can skip. You can kind of directly go to this slide. Okay. Now the variable mu, m is mu, does not appear in the Black-Scholes differential equation. The equation is independent of all variables affected by the risk preferences, and the solution to the differential equation, therefore, is in the risk-free world, which leads us to the principle of risk-neutral valuation. The way I compute is this. So if I apply risk-neutral valuation, what am I doing? I'm assuming that the expected return from the stock price is the risk-free rate. The expected payoff from what we then do is we calculate the expected payoff from the option on maturity, and we discount the payoff today to kind of calculate the option premium or the option price. So three things. We say, okay, we assume that the expected return from the stock price is nothing but the risk-free rate. Second, we calculate the payoff based on this information and whatever else we can have. We calculate how much is the payoff from the option and maturity, whatever is the maturity date. And then once we know the payoff from the option and maturity, we discount it back to today and say, okay, therefore this is the price of the option. Oh, shucks. If this does not show up, then I have a problem. Okay. God. Oh no. Just 1 minute. Let me just try doing something if that works, because this does not show up out here. And then I will really have a problem in that. I'm just trying to kind of convert it into a PDF file and upload a PDF file and see if that helps me. Because this stupidly canvas is not allowing me to do this. So browse. I hope this works. I hope the PDF file works. Okay. Yeah, this works. Okay, good. Thank God this works. Hi, can you see my screen now? Can you all see my screen? Some of you can, some of you can't. Okay, you can see my screen, then it's fine. Then I can kind of continue. Good. Then I'm safe. So this is what the Black-Scholes price is. Right. So this is what the Black-Scholes pricing formula, Black-Scholes merchant option pricing formula is. So now let me let me explain what each of the terms are. So C and P stand for the call and the put option prices. C and P are standing for the call and the put option prices. S naught is the current asset price. Okay, one of the other things that we will have to keep in mind is all of this has to be a function of the 5 terms that we started off with. And what are the 5 terms that we started off with? The 5 terms that we started off with are spot, strike, interest rate, time to maturity, and volatility. These are the 5 terms that I have and nothing else. So once I look at the 5 terms that we can start off with, I get this. C is nothing but S naught. I'm sorry if I solve that equation, and this is the formula that you all should know. C is nothing but the Black-Scholes equation is nothing but S naught into ND1, and I'll explain what they are. ND1 minus K to the power of minus RT, ND2. And the put option formula is therefore, if you apply If you take this formula and apply the put call parity equation and then solve from there, remember we calculated the put call parity yesterday or day before, and therefore you can calculate from there. You will get the put option formula to be k to the power of minus RT, n of minus D2 minus Sn of minus D1. What is D1? You can see down there what is D1. D1 is kind of a combination of again the 5 terms: spot, strike, interest rate, time to maturity, and volatility. Right? S0 is the spot, K is the strike, R is the interest rate, sigma square is volatility, D is time. So obviously, if I know these 5 variables, which is what I obviously would know, I can then compute my D1, which is nothing but a numerical value based on this. And similarly, I can compute D2, similarly I can therefore go and compute D2, which is also kind of a function of that. Now D2 can be simplified to be written down in the order that I have, which is D1 minus sigma root T. And what is this? What is the problem that I have solved? The problem that I have solved is down there. Remember, my ds is the bit highlighted in yellow. My ds is mu s dt plus sigma s dz. And the call option for, remember, the payoff function is max of the expected value of st minus k at 0, and the put is the maximum of expected value of k minus st at 0. Right? There's one small thing that I have not done, which is this is the payoff on maturity. To calculate the premium, I will have to calculate the present value of this, which I can do and not a problem, and that is how I calculate this function. Right? So now, the next thing that I want to do is to show you, you see, in the, not yesterday, day before, I showed you, and I kind of explained to you, just pure theoretically, what will happen if you change the various parameters to the option price. Remember, I showed you what happens when you change it, what happens to the option price, and when you change the various parameters. What I'll do now is I'll now verify or justify the same using this function and using the table from here. So what I've done first is I've written everything down, but what I've done first is the yellow part, the highlighted part, is from the previous slide. The only difference is that I've just done one small difference. My first two, my C and my P, does not undergo a change and they are as it is. My C and my P is written exactly in the same manner. The only change is D1 and D2 was written concisely out here. I have expanded D1, D2 because there are 3 terms and I've just simplified those 3 terms and I've written D1, D and D2 in that order. By simplifying it, and I'm kind of, wherever there's a division, multiplication and all that, I've taken care of that and I've written that in that manner. And if you look at it, if you compare it from here, say take this. The first term will be log of S0 by K divided by 1 by sigma root T. That is what I have, 1 by sigma root T into log of S by, okay. So there's a small not typo, but mismatch, which is in this slide, on this slide, I've taken X as the strike price, whereas in the previous slide, I had K as the strike price. Right? So that is basically that is the thing, and therefore you can see that all I've done is I've just written it expanded. Okay. Now let's see what happens in each of the cases. So my first case was when the spot price increases, right? Now tell me, when the spot price increases, and let's say the spot price goes to infinity, what happens to D1? You know, I've said call increases, put goes to 0, but why does that happen? So what happens to D1? If S goes to infinity, what happens, and everything else is held constant, what happens to D1? S goes to infinity, what happens to D1? Everything else is constant. In that equation, what happens to D1? What is the value of D1 if S goes to infinity? If S goes to infinity, what happens to D1? What is, if S goes to infinity, what value does D1 take? Remember, everything else remains constant. What is the value of in D1 then? What do you think will happen to D1? If S goes to infinity, what happens to D1? Where do you think D1 goes to? Guys? S goes to infinity, what happens to D1? Somebody. Come on, it's not that difficult. I've written out the equation for D1. I'm saying S goes to infinity. What happens to D1? What happens to D1? Somebody. The equation of D1 is given to you. I'm saying S goes to infinity. What happens to D1? What happens to D1? Come on, all of you. Somebody, please. If S goes to infinity, what happens to D1? Are you all getting my question? Do you understand my question? Come on, please. Do you understand my question? Guys, can you understand my question? Somebody. I mean, how do I otherwise I just keep on saying and I will not know whether you all understand or not. I'm saying I've written down my equation of D1. As S goes to infinity, what happens to D1? Can somebody please at least tell me whether you heard the question and got the question? Oh God. If S goes to infinity, what happens to D1? Okay, I'll type it out also for you all. Can somebody now please answer? Okay, let's see what you have to say. No, just look at the equation. So can you read this equation D1? I have the 5 terms. Sigma t, this is square root of t, log of s by x, r, square root of t by sigma, plus sigma root t by 2. Now, if that is the case, and now I'm asking the question that if s increases to infinity, what happens to d1? If s increases to infinity, what happens to d1? Exactly, d1 goes to infinity. That's the simple question I'm asking you, and you are like taking 10 minutes, so probably 5-7 minutes to answer that. And similarly, if d1 goes to infinity, d2 also goes to infinity, right? Now, n d1, what is n d1? What is the function n? N is the n d1 is the area under the normal distribution up to the point d1. Now, the good thing is I do not have to calculate this because we have this normal distribution tables which already have computed all of this, and therefore I can calculate, I can just look it up from the normal distribution table to look at that. So the ND1 is nothing but the area under the normal distribution table up to the point D1, right? So, but what is D1? As we said, D1 is plus infinity. So if D1 is plus infinity, then ND1 is the entire area under the curve, which is basically therefore ND1 is therefore nothing but plus one, full 1. ND1 becomes 1. ND1 then kind of become 1. If ND1 is 1, and therefore ND2 is also 1. So look at this equation. Look at C. C becomes S into XC by S minus X to the power of minus RT. X has remained constant. R and T are constant. Therefore, there is no change in that. And therefore, as S increases, C increases. Now, if D1 has gone to plus infinity, minus D1 therefore has to go to minus infinity. And therefore, now minus infinity, as if d1 goes to, if the area under the curve the entire up to plus infinity is 1, the area on this side up to minus infinity is 0 because that's the starting point. So n of minus infinity is 0. So therefore you have x in the power of minus rt into n of minus d2, which is 0. So that is 0 minus s n of minus d1, which is also 0. So therefore the put price goes down and the put price obviously goes towards 0. Similarly, as x increases, realize as x increases, d1 goes to minus infinity, and therefore d2 also goes to minus infinity. If d1 and d2 go to minus infinity each, then nd1 and nd2 go to 0 each, which means the call price goes to 0. What happens to the put? The put up the since d1 and d2 go to minus infinity each, therefore minus d1 and minus d2 goes to plus 1 each, which means n of the d1 and d2 go to minus infinity each, which means minus d1 and minus d2 go to plus infinity each, which means n of minus d2 and n of minus d1 go to plus 1. So you have x to the power of minus rt minus s. But again, remember, only x is increasing, everything else is remaining constant. So therefore, the put option increases and the call option, as I said, goes to 0. What happens when R increases? What happens to D1 when R increases? So in the same way, tell me what happens to D1 when R increases? Where does D go? D1 go? When R increases, where does D1 go? D1 in absolutely D1 increases to, and D1 increases to plus infinity because R is plus infinity. So n of then D1 is 1. So it becomes it becomes S, and D1 is 1. D2 also increases, and therefore D2 goes to plus infinity. So n of D2 also goes to 1. But one small thing is now you have to be careful. What is d n of D2 multiplied by x e to the power of minus RT? R has gone to plus infinity, which means e to the power of minus RT has gone to e to the power of minus infinity. And e to the power of minus infinity is by definition 0. So basically the second term becomes 0. So the call price then goes to S. And as you can see, as R increases, the price of the call increases, and the maximum value it can go to is S. What happens to the put? As D1 goes to infinity, D2 goes to infinity, by the same logic, ND minus D1 and minus D2 go to minus infinity each, which means n of minus D1 and n of minus D2 go to 0 each, and hence the put price goes to 0. So the call price increases, the put price decreases, and also the call price increases not to an infinite level, but to the value of the spot price. It does not go higher than the value of the spot price. So there's a limiting condition as well. Now, what happens when sigma increases? Sigma is a little more complicated. So what happens when sigma increases? What happens to D1 and what happens to D2? When sigma goes to infinity, what happens to D1? What happens to D2? As sigma increases, just work around that thing. Tell me what happens to D1, what happens to D2. D1 and D2 go to 0. No, why should they go to 0? They don't go to 0. And that's precisely why I've expanded it and written it in that fashion. Otherwise, yes, there is a problem of thinking that it can go to 0, but obviously it is not the case. If sigma goes to infinity, what happens to D1 and D2? They don't go to 0. Okay, that much I tell you. So where does it go to? You see, D1 goes to plus infinity, D2 goes to minus infinity. As D1 and as sigma increases to infinity, D1 goes to plus infinity, D2 goes to minus infinity. How? So look at the first term. What is the first term in D1? There is a 1 by sigma. Sigma goes to infinity, which means 1 by sigma goes to 0. So the first term does not contribute. That goes to 0. The second term is R root T divided by sigma. Again, as sigma goes to infinity, 1 by sigma goes to 0. So the second term goes to 0. But in the third term, sigma is in the numerator. So sigma goes to infinity, sigma root T also goes to infinity. Therefore, D1 goes to infinity. And by the same logic, D2 goes to minus infinity because the first two terms go to 0, but the last term is sigma with a negative sign, so it goes to minus infinity. Right? So you have D1 go to plus infinity, D2 goes to minus infinity. If D1 goes to plus infinity, D1 and D1 goes to 1. If D2 goes to minus infinity, and D2 goes to 0. Now let's go and plug it in. And therefore, you see what? Call becomes equal to just spot S. Because ND1 goes to 1, ND2 goes to 0. So therefore, this only becomes S. And when the put D1, D2 goes to minus infinity, which is minus D2 goes to plus infinity. D1 goes to plus infinity, which means minus D1 goes to minus infinity. So by the same, then for ND1 and ND2 will work out in that manner. So your put increases and put goes to x to the power of minus RT, but the rest of the terms don't matter. The rest of the terms go to 0. So both of them increase. The call price increases to a level of S. The put price increases to a level of x to the power of minus RT. And why am I saying it increases? Because you realize ND1 is a number less than 1. So if you multiply S by ND1, you will get a number less than S. So obviously the maximum value this can take is when ND1 is 1, when S is equal to S, ND1 is equal to S. On this side, X is positive, e to the power of minus RT is positive, and ND2 is also 0 or positive. So if it is positive, then all three are positive. So you are subtracting a positive number from that. But if you are not subtracting, if the minimum you are subtracting is 0, therefore the value of the call increases. By the same logic, the value of the put also increases because you are subtracting 0 against, alternately you would have subtracted a positive number, which would have definitely brought down the share. Right? So ND1, and so basically, therefore, the as sigma increases, the call price increases, and the put price also increases. But the call price increases to S, the put price increases to x to the power of minus RT. Right? Finally, what happens with T? Now, this is a little more interesting. When T increases, what happens? Now that I've told you what happens with sigma, and I've shown you how it happens. If I increase T, what happens? If T goes to infinity, what happens? What do you think will happen when T goes to infinity? What do you think will happen when T goes to infinity? Right. When T goes to infinity, what happens? When T goes to infinity, what happens? T goes to infinity, what happens? What happens to D1? What happens to D2? D1 is actually straightforward, and D2 is a little more complicated, but D1 is quite straightforward. Right. What happens to try what happens to D1? T goes to infinity, what happens to D1? What do you think will happen if T goes to infinity? Okay, let's look at D1. When T goes to infinity, what happens to D1? Guys, please answer. Please try. Because if you think I will do it for you, I can. But at the exam, you will have to do it. So how will you answer it? I can easily do it. I know exactly what will happen. And I've done it so many times that it is kind of very obvious to me. But you guys should attempt it. So what happens to D1? If t goes to infinity, what happens to D1? If t goes to infinity, what happens to D1? If t goes to infinity, what happens to D1? Oh, God. Guys, look at this equation. If t goes to infinity, what happens to this equation? What happens to D1? If t goes to infinity, what happens to D1? Absolutely, you're right. So I mean, why do I have to ask you like 100 times before you answer? I don't understand. If you don't, I mean, or alternately, tell me you guys don't want to answer. I will simply go through without bothering. It's quite quite disconcerting to kind of keep on asking the same thing and you all just don't bother to respond. Okay, if d1 goes to infinity, therefore we know nd1 will go to 1, so that is easy. Now d2 is not that straightforward because d2 can be plus infinity or minus infinity. Why? The problem in d2 is, you see this value, the first term, there is a square root of t in the denominator. Therefore, t goes to infinity. No, sorry. What did I say? This is wrong. D1 does not go to 0. D1 goes to infinity because this term goes to 0. But here my t, square root of t is in the numerator. So this goes to infinity, this goes to infinity, the sum of two infinity terms, this obviously goes to infinity. Sorry, that was wrong. I kind of did not see that properly. I read the word infinity and I took it accordingly. Realize that in D1, the first term goes to 0 because I have the square root of t in the denominator. In the second and the third term, my square root of t is in the numerator. So as t goes to infinity, those two terms go to plus infinity each. And therefore, the sum goes to plus infinity. Okay. Now, when d1, but the rest of it was correct, was I saying? So when d1 goes to plus infinity, nd1 goes to 1. So that is easy. Now, d2 is a little more complicated because the first term goes to 0. 1 by sigma root t, as t goes to infinity, square root of 1 by infinity goes to 0. So the first term goes to 0. The problem is in the second term. You have the r by sigma into t, root t, which is sigma, which is infinity. And then you have sigma by 2 into root t, which is also to root t is infinity. But that is negative. So you have r by sigma t, r by sigma minus sigma by 2. And then if r by sigma is greater than sigma by 2, this term will d1 will go to plus infinity. If r by sigma minus d by sigma by 2 goes to minus infinity, this term will go to minus infinity. So I do not know where d2, it can't go anywhere else. but I do not know where it exactly goes. It can either go to plus infinity or it can go to minus infinity. Now, okay, I don't have too much of a problem with it. I can get, I mean, normally I would have a huge problem with that. But in this context, I will not have too much of a problem. I will get away with it. And how do I get away with it? The way I get away with it is this. You see, if D2 goes to plus infinity, ND2 goes to 1. If D2 goes to minus infinity, ND2 goes to 0. Okay? Now let's look at the call equation. D1 goes to plus infinity, as we said, and therefore ND1 goes to 1. So S into ND1 goes to S. What about the next term? I do not know what value ND2 takes. I know it takes either 0 or 1. But realize there's a term before that, x e to the power of minus rt. R is constant, but t has gone to plus infinity. So as t has gone to infinity, e to the power of minus rt has gone to minus infinity. And therefore, e to the power of minus infinity goes to 0. So whatever that term is, you are multiplying by a 0, and hence the second term does not matter. So as time increases, the value of the option increases and becomes equal, and at the maximum becomes equal to the spot price S. What happens to the put? Realize as D1, now I do not know whether D2 goes to plus infinity or minus infinity. And therefore D minus D2 goes to minus infinity or plus infinity. So again, n of minus D2 goes to 0 or 1. But I do not bother about it, because again, remember, there is a coefficient of e to the power of minus rt. T goes to plus infinity. Therefore, minus rt goes to minus infinity. E to the power of minus infinity goes to 0. So the first term essentially goes to 0. So P becomes, and then D1 has gone to plus infinity. So minus D1 goes to minus infinity. And therefore, S again, n of minus infinity is 0. So you get 0 minus 0, and therefore the value of the put goes to 0. So therefore, as the P increases, call increases, put value goes to 0. Now, if you now think of it and go back and check with what I told you yesterday, day before yesterday, theoretically, that prices will increase, this will happen. In the first part, when we're talking about the properties of options, this is exactly what happens. And this also happens in that framework. And therefore, what I said that day is now justified using the formula as well. So using the formula, I can, and mathematically I can justify the computation or the fact that the values will move in a certain direction. And that is so apart from the valuation argument of Black-Scholes, that the directional move is the other way of other part of it. Now, one other question I want to kind of highlight out here, that there is something called, so if I go back to the previous slide, you see that I need a sigma. What is sigma? Sigma is the volatility, right? Sigma is volatility. Now, how do I estimate sigma? Remember, we have said this earlier. One way to estimate sigma is to calculate the based on historical data. So use some kind of model, which could even be simply, as I said, based on historical data, and I can compute the value of sigma from there. That is one way of doing it. The other way of, so and obviously that is what is called as the time series based approach of doing this. Then there is another way of doing it, which is essentially called the stochastic process based approach of doing it, which is also doable and which is a bit fairly which is not a simple straightforward, which is a complicated model. There is a third way of doing it, and that is what is being talked about out here in the next slide, which is what is called as implied volatility. Why do we call it an implied volatility? We call it an implied volatility simply because, you see, in that period, now what is happening? I'm using the volatility to calculate the price. I use the volatility to calculate the price, and therefore I can calculate the price. So it is like I have an equation and five parameters, I use the 5 parameters to calculate the value of the equation on the other side. Right? So that is how I calculate that. Now, what I can do out here is, if I give you the value of, so if I go to the previous slide actually, and even this slide will also do. So now in this equation, if I give you the value of the call option, if I give you the value of the call option and then give you 4 of the other 5 terms, which is spot, strike, time to maturity, and interest rate. So remember, I don't give you volatility, I give you 4 terms: spot, strike, time to maturity, and interest rate, and I give you the price of the option. Therefore, one can use the simple algebra and can work backwards to find out the value of sigma, because effectively I will end up having one equation in one unknown, the unknown being sigma, and therefore I can calculate the value of sigma to kind of get that. So therefore I can easily compute the value of sigma from there. I have calculated the value of sigma from there to kind of calculate the fact that there's one equation in one unknown, and I've got the value of sigma. And that sigma is what is referred to as the Black-Scholes, as the implied volatility. So implied volatility of an option is the volatility for which the Black-Scholes price equals the market price. Which means what? I take the market price, I take the Black-Scholes model, and I say the price is equal to the Black-Scholes market price. And to calculate the price, I take I know the 4 other factors, which is spot, time to maturity, spot, strike, time to maturity, interest rate. And therefore, using this, I can work backwards. I can work to find out what the value of the interest rate is. Now, this is what is called as the implied volatility, and traders very often quote these implied volatilities in the market rather than the dollar prices. Now, and obviously to calculate this, you need to have a risk-free rate. So I've given you that example where in the Indian market, this has been computed, and this is just to show you that thing. But there is one small thing that I would want to highlight to you out here. Obviously, if I want to calculate this implied volatility, I would therefore need to know the option price. I can only compute this if I know the option price. If I do not know the option price, I will not be able to compute this. I can only compute this knowing the option price. Now, to know the option price, I would therefore need to know the volatility in the market. Because again, it's a circular problem. I will not be able to calculate the option price if I do not know the volatility. So effectively, what you're arguing out here is a bit strange, because what you're saying is, I know the volatility, or I somehow know the volatility so that I can calculate the price, and then I'm using the price to calculate the volatility back again. What is this big deal? Well, the point is that not everybody will have the ability to calculate the volatility because of the complexity involved, both in terms of data availability and the data requirements and all of that, and the processes. So hence, what do? What we are saying is, let's say there is a big bank, there is a big player in the market who has the ability to go and estimate this process and estimate the volatility directly and price the option. Now, as a small player, that person does not tell me what is the estimate of volatility that he or she has. What I can see from the market is what is the price of the option. Given the price of the option, I work backwards to find out an estimate of the volatility that person is using. And that is what I'm doing. What is the problem? What is the challenge in this whole process? Right? What is the volatility that I will? So what I do is I kind of say, okay, you have calculated the price, but you're not telling me what the volatility is. Now, given your price, I'm working backwards to have an estimate of your volatility. Now, is this going to be correct? Well, it is going to be correct if you also use Black-Scholes and make the same assumptions that I do. In practice, I do not know what are the assumptions that you have made. And hence, to that extent, there can be a small difference in the prices that can happen. And hence, the estimate of volatility can be slightly different. Having said that, The point is that since I do not have an ability and the means to estimate volatility directly, and it is probably too complicated for me to do it, I am estimating it using this some approximation. This is a reasonable approximation, and this also tells me what is the market's expectation given these are based on the market prices. So, what is the volatility that the market implies based on the prices at which it is trading? And hence we kind of argue or say this is the implied volatility in the market. So that is the meaning of this term, implied volatility. And that is what we kind of compute as a part of this. Now, I will talk about in the next slide. I do have from historical data, and I'll quickly run you through that before I show you some examples. But the point that I will actually point is there is another point that happens which is relevant out here. And then that is not every time you want to find out the volatility, you want to price a new option for, so you want to price a call option on a certain stock. Now there may not be any call options trading in the market at this point in time. There will be only put options trading. What will you do? Well, as long as the underlying asset on which you want to price the new option is the underlying asset for the option which is trading in the market. So, I am looking at the volatility. Please understand and please remember that what you are looking at is the volatility of the asset and not volatility of the option. So therefore, it does not matter whether you are inverting a call option or a put option, as long as the underlying asset is the same. As long as the underlying asset remains the same, it does not matter whether it's a call option or the put option. And that is how you would be able to compute therefore you can compute the value of the call option compute the value of the volatility as long as that asset is used as an option as an underlying in some option, and then from that volatility number that you get, you can go and price your new option as well. So that is the utility that you kind of get in that process. Now the alternate way is basically to calculate it from historical data. So what you do is you kind of calculate the returns, take the observations, and then you calculate the continuously compounded return in each case, as I have done, as log of SI by SI minus 1, and you calculate the standard deviation of SI, and you calculate the standard deviation of the S, of the standard deviation S of the U's. UI is given by this. So the historical volatility estimate is therefore given by sigma by root tau, and the standard error of estimate, after you are estimating it from data, the standard error of estimate is given by sigma hat, which is what is estimated, divided by square root of 2n. That is the error of estimate, whereas the historical volatility estimate is then taken as UI is the this S is the volatility of U, standard deviation of U divided by square root of tau, where tau is the number of observations at intervals of tau years. So tau is the number of observations that you have, number of years that you have. So you divide it by the square root of number of years. There is also this thing that comes in, which is volatility is obviously much greater when the market is open than when the market is closed. So basically, when the market is open, the expectation is the asset is trading, and if the asset trades, the volatility is typically much higher. If the market is closed, then the volatility will not be as high. And this is the reason why the measurement is typically done in trading days and not in calendar days. So remember that what happens is that obviously some days there will be no trading. For example, on the weekend, markets are closed. So if you take calendar days includes the weekend. But for trading days don't include the weekend or holidays or whatever. So therefore, it is typically measured in trading days and not in calendar days when options are valued. So, but you will report volatility in a per annum basis, like everything else. You would want to report it on an annual basis, per annum basis, so that it is comparable. So what do? You calculate the per trading day volatility per trading day, and you multiply it by the square root of the number of trading days. So therefore, volatility per annum is nothing but volatility per trading day multiplied by the square root of the number of trading days in a year. And the approximate number of trading days in a year is taken to be 252. How does that number 252 come about? Realize we have a 365-day year, and there are 52 weeks, so 104 days of Saturday, Sundays when the markets are closed. So 365 minus 104, that is 261, and then there are about 10 days of or 9 days of holidays that are accounted for approximately, on which markets are closed, and therefore you end up getting 252, and that is taken as an average number of days in a year. So therefore, the number of trading days in the market is open. So that becomes your average number of trading days per year. You multiply the volatility per trading day into the square root of the number of trading days per year to kind of get the volatility per year. That is how it is quoted. Okay. Finally, obviously, remember one of the assumptions that I had was that there was no dividend during the life of the option. However, you can have dividends during the life of the option, and then one can account. I mean, if there are, and if it is known, you can kind of account for it in some manner. So European options and dividend paying stocks are simply valued by substituting the stock price by an amount which is stock price less than the present value of dividends into the Black-Scholes Merton pricing formula. And the dividend should be there because the argument is the dividend is the expected reduction in the stock price expected. So let me show you one example. Let's say that you have a European call option on a stock when there are X dividend dates in 2 months and 5 months time. So I have a dividend which is expected in 2 months, and then I have a dividend which is expected in 5 months. And each of the dividends is expected to be 50 cents, $0.5. The current market price is 40, the exercise price is 40, and the stock volatility is 30% per annum. The risk-free rate of interest is 9% per annum, and the time to maturity is 6 months. And therefore, as you see, the first dividend comes in 2 months, and the second dividend comes in 5 months. Both of them come before the option expiry of 6 months, and therefore that has to be adjusted for accordingly. So what do? The first thing that I do is I calculate the present value of the dividend. I get 50 cents after 2 months, and I get 50 cents after 5 months, and discount them at 9% each because that's the interest rate. So the present value of the dividends works out to be 0.9741. So what is the current value of the spot? The spot in the market is 40. Therefore, the adjusted spot is going to be 40 minus this one. So I calculate the present value of the future payments, future dividends that we know of. Obviously, is this the only 2 dividends? Can't be, because there has to be an expectation of a dividend and all that. Right? So I simply take the present value of the dividend, I subtract that from the current spot price, and therefore I end up getting the current spot price to be 39 point whatever, 9741. So that becomes 39.0259. My strike is 40, interest rate is 9%, volatility is 30%, and the time to maturity is 6 months, 0.5 years. So I plug these numbers in. If I plug these numbers in, all I've done is I've then gone and calculated my D1. I've calculated my D2. And then once I've calculated my D1 and my D2, I have looked up the normal distribution table to find out what the value of ND1 and what the value of ND2 is. Once I know the value of ND1 and ND2, I have plugged those numbers in the call price equation, and I found out what the price of the option is. So basically, this is an option. So what does this say effectively? That I will pay 3.67 today to kind of retain the right to buy a stock, right? So by paying 3.67 today, I'm retaining the right to buy a stock at 40 in 6 months' time. When the current market price is 40, the volatility is 30%, and the interest rate is 9%. And I also know that in 2 months and in 5 months' time, the stock will pay a dividend of 0.5 each. So they're keeping all of this in mind. The cost that I will have to pay, right? So therefore, the cost that I have to, how much will I have to pay? 3.67 is the cost that I have to pay. I mean, accounted for all of this, right? And this is how I got it. What happens if it's an American call? Well, as you saw yesterday, and as I showed you, for an American call on a non-dividend paying stock, an American call on a non-dividend paying stock should never be exercised early. It does not make sense to exercise an American call on a non-dividend paying stock earlier than maturity. Why? Because by holding on, you do not lose anything. In fact, you have access to all the exercise possibilities. So you should hold on to it. Now, an American call on a dividend paying stock should only ever be exercised immediately before the ex-dividend date. Ex-dividend date is the date on which the dividend is paid. So just before the dividend is paid, you should exercise a dividend American call on a dividend paying stock. Now, let's say there are multiple dividends. So the dividend is being paid at T1, T2, T3, Tn respectively. Now, early exercise can be optimal, and this is obviously the first point holds that if the stock is non-dividend paying, do not exercise early. Do not bother about exercising early. You exercise, you only think about exercising early if it is. You can think of exercising early if it is a dividend paying stock. And what do you then do? And you have to. It is optimal only if this condition is met. That is at the time TI when the dividend is being paid, the value of the dividend at that time. So at time TI, the amount of dividend that is being paid, the value of the dividend is greater than this function where K is the strike price, R is the interest rate, TI is the time when the dividend is being paid, the current dividend is being paid, TI plus 1 is the next dividend payment point. So if this condition holds, if the dividend is greater than this, then obviously early exercise is feasible. If this does not hold, then you should never exercise. You should hold on the call till maturity. Now there is also an approximation that Black has suggested, but this is a little more complicated because obviously there is this whole thing. So he says that for American call dividends and American call options, you can handle it by saying let's price 2 European options and take the price to be the higher of the two. And what are the 2 European options? The first is an European option with maturing at the same point in time as the American option. And therefore, the early exercise is not really accounted for. And early exercise is kind of discounted. And the second is an European option for an option that matures just before the dividend payment date. So basically, I take an option, I price an European option for the entire life of the American option, irrespective of the fact that there is a dividend payment that is happening in between, on one hand. And on the other hand, I price an option only to the dividend payment point, or just prior to the dividend payment point. And the value of the American option, according to Black's approximation, is the higher of the two. Right? So this is another way of looking at it. Okay, let me show you a few examples before we take the break, and then we will start with briefs. What is the price of a European put option on a non-dividend paying stock? When stock price is 69, strike price is 70, risk-free interest rate is 5%, volatility is 35%, and time is 6 months. So the first thing that you do when you see a problem like this is identify the terms. So your S0 is 69, right? The current S is 69, strike is 70, XK is 70. Okay? R is 25%, P is 6 months, and sigma is 35%. So now you have all these numbers. Right? Right? So I have all the terms. I have spot, strike, interest rate, volatility, time to maturity. So just go and plug it in. You have all the terms. Spot, strike, interest rate, volatility, time to maturity. Plug that in. Calculate the values of D1 and D2. Once you've calculated the value of D1 and D2, put it in the formula and you'll get the value of the option. So this is the call option that they're pricing. So plug it into the call option form. Oh, sorry, this is the put option they're pricing. So plug it into the put option formula, and therefore you get the outcome to be what is the value of the put to be $6.40. What about this? American call option on a stock. The stock price is $70 today, and the time to maturity is 8 months. The risk-free rate is 10% per annum, and the exercise price is $65. Volatility is 32%. Now you have a dividend of 1, which is expected after 3 months, and another dividend of 1, which is expected after 6 months. Again, after 6 months. Right? Your maturity, your call option maturity is for 8 months, and therefore both these options will be exercised, or these, sorry, not options, the options will be, both these dividends will not be exercised. Now, what I want you to show and what we want to see is that this option is not, it is kind of illogical, or it is suboptimal to try to exercise this option early. So in a sense, what we are saying is in this option particularly, with the kind of numbers that are there and kind of returns that are being offered, this option should be held until maturity. You should not exercise this option early, because by holding on to, because by holding on to the how do I do this? I apply the second approach. So what are my dividends? My dividends are 1 each. So my D1 is 1, my D2 is 1. What are the time points of the dividends? So the second dividend is going to be paid at, so time to maturity is 8 months. The second dividend will be paid after 6 months. So the time to maturity, the time between the payment of the second dividend, the time to maturity is 2 months. And the time between the two dividends is 2. One is being paid after 3 months, and the other is being paid after 6 months. So that is 3 months. So now if I take the second one, K1, the K into 1 minus e to the power of P minus T2 is how much? K is 65. Put all the numbers, it is 1.07. Similarly, if I take K into e to the power 1 minus e to the power minus R, T2 minus T1, where T2 minus T1 is 3 months, that works out to 1.6. So what do I see? In both cases, the current dividend is less than the calculated value that I have, and hence it is suboptimal. It is not optimal to exercise it early. On the other hand, if the current dividend was more than this number, yes, you would argue that exercising early might be sensible. It might have its own therefore, what I can show is that it is never optimal to exercise the call option early. Because anything I do, this will be no early exercise that will kind of happen, and it's useless. Right? So I can do both the things. If I have a dividend payment in an European option, I will just simply subtract the dividend payment to the present value of the dividend payment and price that in that manner. if if it is an American option, should I exercise early? Well, to price it, I cannot do this. To price it, I will have to remember the pricing of the American option is only done or only doable by using the binomial tree approach. But the approach will still be the same. I will take out the present. I will discount. I will subtract the present value of the dividends from the spot, redraw the tree from the adjusted spot, and calculate the price of the option like I did yesterday. What I can also do is I can also check using this last bit whether it is at all optimal to exercise, whether I should at all exercise the option early or I should let the option, expire. I mean, can continue on. Sorry, not expire. Hold on the option till maturity. Because remember, in an American option, you obviously have the choice to exercise early, but you may choose to hold it on till maturity. So if you want to hold it on, so should you do that? Is it so? On the other way around, the question: is it optimal to hold on to the option early? Is it optimal to hold on to the option? So is it optimal to exercise the option prior to maturity? Well, you can do this as I've shown you out here in the last slide, and as an example, and I've shown you the formula earlier. If that happens, so I've shown you the formula which says that if that happens, you may decide, you may think about exercising early. If that does not happen, you should not exercise early. And that is exactly what I showed you out here through this example, that if that happens, you should not exercise early. Okay? So that tells you how you can price the option also. And therefore, these are the two ways in which you can kind of price the option. So that kind of takes care of the option pricing bit. I'll take a break here. And I will start with Greeks of the option after this measure of the sensitivity of the options. But before I do that, any questions? Do you have any questions for me? Because please understand this process well, because obviously this forms a significant bulk of the discussion of the whole process. And we will actually, and this becomes this very important in this whole scheme of things. So valuation of options is actually very, very important. And that is what I wanted to kind of show you out here. Any questions? Okay. Yeah. Okay. If there are no questions, let's take a break. Let's take a 15-minute break. Today we are actually much better off. So it's what, about 9 o'clock? No, it's about, yeah, it's 7:30. So it's about 9 o'clock for you, right? No, it's not even 9. So it is going to be, it's just about 8:40, 8:50 for you. So let's join back at 9:05 your time, 5 minutes past 9 o'clock. We'll start and we will quickly do the Greeks of the option Greeks, and then we'll see if we can do VAR also. Okay, or we can kind of do the Black's model, and then I can talk about VAR and swaps tomorrow. Okay. Okay. Let's pause recording. Let's take a 15-minute break, and then we'll come back. Okay. So the next bit is what is called as the Greek letters or the Greeks. Now, what are the Greeks? Very quickly, the Greeks in this context are a measure of the sensitivity of the option of the. So the Greeks are a measure of the sensitivity of the option price. So essentially, we've done the option pricing. We've looked at option prices. How do we measure the risk? So we saw in one way of looking at sensitivity is what we saw in the last part. And what happens as the prices rise, or as the asset price rises, volatility rises, and all that. The question is, how do I measure that, and what can I do with it? And that is what I want to do. That is what I want to kind of look at in terms of the Greek letters. So one way to look at this is I can write down the option portfolio. So this is very, very simple, and what I've done, just to understand this. So my option portfolio value is a function of the spot, time to maturity, interest rate, volatility. There is also strike, but since strike is something which is decided by you, You have not put it in there, but you can put a strike. And then using a simple mathematical argument of a Taylor series expansion, the change in the value of the portfolio pi can kind of be written down in that fashion. And what you therefore see is what I'm saying is a change in the value of the portfolio with respect to spot is delta, with time is theta, with interest rate is rho, with volatility is vega, and I also write down the second order term with respect to spot, and that is gamma. And obviously I can have higher order terms, but I do not go into higher order terms simply because in most cases we will not be able to address most of this. The only one that we can kind of realistically address in all scenarios is delta, the first one. Sometimes we can address the gamma and the others as and when the opportunity arises. So therefore, even if I can compute the higher order terms, what is the real value of doing it? Because I will not be able to solve much of it. So that is why we do not bother looking into that. Sorry. So what is delta? If I look at the first one, what is delta? See, if we look at the graph, the option price and the stock price. So as the stock price changes, what is the, so it is a rate, as I have written out there, the rate of change of the option price with respect to the change in the underlying. So if C is the price of the call option, then delta is nothing but the partial derivative of the change in C with respect to S. And similarly, if it is P put, then it will be delta of the partial derivative put with respect to S. Now, delta, as I said, delta denotes the movement of the option position with respect to the movement of the underlying position. So, in some sense, delta is the speed of change of the option value when the underlying asset value changes. Why is this important? Because of the next point. Because delta is another way of expressing the probability of an option expiring in the money. Realize that if you are an option writer and if the option expires in the money, you will have to pay up. So therefore, if I can find out the probability of the option expiring in the money, I can potentially take action, potentially take protective measures to ensure that I have covered, I have kind of protected myself against a possible payout. Right? Now, one thing I should actually have said out here before I go forward is that option Greeks are only applicable to option writers. It is not applicable to option holders. Why? Because option holders have already paid the premium, and therefore there is no rationale for the option holder to pay anything more. So therefore there is no point of the option holder actually requiring to pay anything more subsequently. It is only the option writer who needs to kind of pay. Now, typically, if you take an at the money call option, an at the money call option is an option whose strike price is exactly equal to the spot price. An at the money call option have a delta of 0.5. So they have a 50% chance of the option expiring in the money and some 50% chance of it expiring out of the money. A deep in the money call option, which is, the price is very, very high. So that, as we defined earlier, in the money, a deep in the money call option will have a delta close to 1, which means that it has kind of a near, it will never have a 1, but it will have a near 100% chance, close to 100% chance of expiring in the money. And by the same logic, a deep out of the money option will have a chance of delta close to 0, which means it has a very low chance of expiring in the money. So if you look at it, this is kind of the rule of thumb that comes in. For a long call, delta can be between 0 and 1. For a short call, between 0 and -1. For a long put, delta is between 0 and -1. For a short put, between 0 and 1. And these are the things. If it is deep in the money, this is for the call. It is deep in the money, 0.75 to 0.1, which means it is deep in the money. It is 0.55 to 0.75. It is kind of just about in the money, slightly in the money. If it is between 0.45 to 0.55, delta is typically taken to be at the money. And similarly, on the other side, if it's 0.25 to 0.45, it is slightly out of the money. If it is below 0.25, it is deeply out of the money. Also for stock, delta is +1. and -1 for short stock. For long stock, it is +1. For short stock, it is -1. Now, what are the values that and these are the things. So remember, these are the same stuff. ND1 is the same that we computed in the Black-Scholes price. So because I have to differentiate, I therefore need the Black-Scholes. Once I differentiate the Black-Scholes, I get the delta. And actually, for each one of them, I'll differentiate the Black-Scholes only. And that is the other utility the Black-Scholes has. Because you could always argue that the Black-Scholes has, the Black-Scholes had this one. What do you say? The Black-Scholes. Why? So why use the Black-Scholes? Because the Black-Scholes only prices the European option. You could have priced the American option. You could have priced the European option and the binomial tree also, which is fair. And the binomial tree is more versatile because the binomial tree can then be used to price. Then binomial tree can be used to price American options also. Well, but you cannot differentiate a tree. So one of the utilities of the Black-Scholes option price is that you can calculate the Greeks also. Now, specifically, the delta for an European option on a non-dividend paying stock is ND1. Delta for a put is ND1 -1. Delta for an European call with an asset that pays dividend at the rate of Q is ND1 into e to the power of -QT, and other one is e to the power of QT into ND1 -1. So one of the things that shows you from here is, remember the maximum value ND1 can take is 1, the minimum value ND1 can take is 0. So therefore, delta of the call can never be negative. Delta of the call can at the worst be 0. Max could be +1. Similarly, delta of the put is ND1 -1. ND1's maximum value is 1, which means the maximum value for the ND delta of the put is 1, and it is negative otherwise. And it makes sense also because as the asset price increases, option price likelihood of option price increases. Increase in option price is nothing but an indication of increase in the probability of option exercise, and therefore the delta of the call will increase, and the delta of the put will decrease the other way around. So that is how you can compute the delta, and then you can go back to this slide and kind of compare that whether it is in the money, out of the money, or whatever it is. Now you can also have something called the delta, position delta, or delta of a portfolio of options. Why should it, if you have a portfolio, why should you just look at delta of one option, but the entire portfolio, or other derivatives dependent on a single asset, S, and the portfolio value is 5. So what you look at is a change in the portfolio value with respect to change in S. So delta of the portfolio can be calculated from the delta of the individual options in the portfolio. So what do? I calculate the individual deltas. Let the weight of the portfolio consists of WI options of the option, WI of quantity of option I. Then essentially delta I is delta of the option I. Then ith option. Then essentially the portfolio, the position delta is summation WI delta I. That's a straightforward simple thing. So let me show you one simple example as to how it happens. So let's say somebody in the US has the following 3 positions on Australian dollar. A long position and 100,000 call options with a strike price of 0.55 and expiration date in 3 months. Delta of each option is 0.533. Short position in 200,000 call options, strike price of 0.56 and expiration date in 5 months. Delta of each option is 0.468. And finally, a short position in 50,000 put options with strike price of 0.56 and an expiration date of 2 months. Delta of each option is minus 0.508. Realize all of them on the Australian dollar, and therefore I can do it. So therefore, what is the delta of the whole position? It is 100,000 into 0.533 plus 200,000 into minus 0.468. Remember, I've shorted it. Let me minus, and then the minus. The put again is a put. I'm shorting the put, so minus into 50,000. Into the delta is of the put is minus 0.508. That is, and therefore I added up, and it becomes minus 14,900. What does this mean? This means that if you want to kind of balance this, so for if the dollar Australian dollar moves up by 1 unit, the person might stand to lose $14,900 because of this option position. So therefore, if he wants to cover himself or protect himself, what does he do? He says, okay, I will hold $14,900 in cash. So if I hold $14,900 in cash, well, the asset price moves up by option, Australian dollar moves up by 1 unit. My loss is $14,900, but I have cash of $14,900 with me. So my resultant cash is a resultant position is there is no change in my resultant position, and hence I kind of have my long position gets offset with the short position, and therefore I kind of have a neutral position. That is what the utility is. A position now. This is all the hedging schemes that you have, and therefore this is a risk argument. So if you have a delta of 0, it is kind of referred to as being delta neutral. So basically, if I can create a portfolio such that for an increase in the spot price, there is while the option price changes, but effectively the portfolio value does not undergo a change. So the benefit out here is offset against the loss out there. That is essentially what I get to a delta neutral position. Now, because the delta changes, the investor's position remains delta hedged only for a short period of time. So the hedge has to be readjusted continually, and this is what is known as rebalancing. So this readjustment is what is kind of known as rebalancing. And if you want to kind of do it on a continuous basis, this is what is called as dynamic hedging or the dynamic hedging scheme. How can you hedge for futures? Remember, can I hedge for futures? The answer is yes, I can hedge for futures also. And to hedge for futures, the delta of the futures contract is to the power of minus R minus Q times T with times the delta of the spot contract. So therefore, if the position required in futures for delta is therefore what is this number multiplied by the number of times required in the corresponding spot contract. Unlike the options contract, here it is multiplied by corresponding times multiplied by the spot contract. The next one is gamma. Gamma is the rate of change of delta with respect to the change in the underlying asset. So it is a change of delta with respect to with the underlying asset, or the change in the second derivative of the change in the. So it's the rate of change of the portfolio with respect to change in the underlying. Now, if gamma is small, delta changes slowly, and adjustments to keep the delta neutral, adjustments that you need to do to keep the option portfolio delta neutral needs to be made only very, very sparingly, very rarely and frequently. If gamma is large in absolute terms, delta is highly sensitive to the price of the option, and therefore rebalancing needs are very high. So you can look at gamma in two ways. It is as an acceleration of the option position with respect to the underlying stock price, or essentially how the delta changes or the change in the delta. So in some way, what gamma does is gamma works as an early warning system that delta is about to change. Now, interestingly, both put and call have positive gammas. Gamma cannot be negative. And deep out of the money and deep in the money options have near zero gamma, because the likelihood of the delta change is very, very low. And therefore, for all practical purposes, gamma tends to peak around the strike price. So gamma tends to peak around if it's an ATM option, gamma tends to be very high. As it becomes deeply in the money or deeply out of the money, gamma tends to kind of go down to zero. So this is the graph that we can kind of follow. Now, as you can make a portfolio delta neutral, you can also make a portfolio gamma neutral. What can you do? So what you can do is you first correct for a position in the underlying asset that cannot be changed continuously when delta hedging is used. An option on the underlying asset. So while delta can be hedged using cash or underlying asset, to hedge gamma, you need to use an option. Now you cannot use the same option because then it will cancel each other out. So you use a different option. You use a different option, but on the same underlying, because the linkage has to be there. So you use a different option on the same underlying. I mean, and that to kind of get it to zero. So what delta neutrality protects you from relatively small changes between rebalancing. So between the rebalancing, delta neutrality will kind of help you to be protected in that period. Gamma neutrality protects you from large changes between the in the stock price between the rebalancing times. So if you say I will rebalance once a week, and if the stock price movement is not very high, then delta neutrality is good enough. On the other hand, if you're changing, if you're again for 1 week, but it's very volatile, the changes are very high, then you would actually need to be gamma neutral. How do you make a portfolio delta neutral that has a gamma of minus 3000, for example? So let's say the delta and gamma of a traded option is given to you. I mean, the values can be computed. The portfolio can be made gamma neutral by including in the portfolio a long position. So he's got a gamma of 3000, right? Minus 3000. So, and a gamma is 1 point, and the gamma of one option is 1.5. So how many options do I need to buy? And I have to basically balance 3000. So my portfolio should have a gamma, my other side of the portfolio, the hedge portfolio that I'm creating should have a gamma of 3000. One option has a gamma of 1.5. Therefore, my total gamma has to be 3000. So 3000 divided by 1.5. Therefore, 2000 options. If I buy 2000 of the options, my gamma will become 3000, and therefore I'll become gamma neutral. But I have a problem with that, because the moment I buy 2000 gamma, 2000 options, my delta, which was originally delta neutral, will now increase because this has a delta of 0.62. So 2000 into 0.62, so my delta position becomes 1240. Therefore, I would also need to buy 1240 units of the underlying asset. Oh, sorry, this has become 1240 is the positive delta, so I need to reduce it. So therefore, I would need to kind of sell 1240 units of the underlying asset from the portfolio to keep it delta neutral, because now I have an excess delta. So obviously, I would now need to reduce it. I would need to sell the portfolio asset from the portfolio to keep it delta neutral. Because in the process of trying to become gamma neutral, I have become delta. I have from delta neutral, I have moved into a delta position. So therefore, I will actually have to adjust for it accordingly. Right? Now this is the, so I'm not going to do the, I'm not trying to do the, what do you say, the differentiations. But if you look at it, the call for a put or the call, the gamma is the same, which is the non-dividend paying stock, with n prime d1 divided by all of that, where d1 is exactly what we had earlier. And what is n prime? N prime is nothing but the partial derivative of n, which is nothing but the density function. Remember, if capital N d1 is the cumulative normal density function, n prime is nothing but the probability density function. So n prime d1 is basically nothing but the probability density function, or the probability, effectively the computation of the probability at the point d1. And if it is an asset, if it is an asset which pays dividend at rate q, there will be a q to the power of qt multiplier, and in your d1 will also have r minus q. So that is an adjustment that will happen in the process. So if I want to show you, give you an example, look at this example. I have a 4-month put option on the stock index. The current value of the index is 305. The strike price is 300. Dividend yield is 3% per annum. Risk-free interest is 8%. Volatility of the index is 25% per annum. So what do I have? My S0 is 305. My strike is 300. My dividend yield is 3%. Q is 3. R is 8%. Sigma is 20.25, 25%. And gamma is 4 months. Sorry, time is 4 months. I'm sorry, time is 4 months because it says up there, right? So what is the gamma of this option? N prime d1 into e to the power minus qt divided by s0 and all that. Plug all these numbers, you get gamma of 0.00857. What does it mean? It means that if the index increases by 1 unit, so the option index increases from 305 to 306, the delta of the option, the gamma will increase, which is essentially the delta of the option will change by 0.00857. So the delta of the option changes by a very marginal amount of 0.00857. Now, this is what will happen if you have a slightly positive gamma. This is delta S and delta portfolio. The gamma curve will be like this. And if it is a slightly negative gamma, it will kind of get flipped around and it will be the other way around. On the other hand, if you have a very large gamma, positive or large negative gamma, then you can see that these numbers will essentially be the curve will still be similar, but instead of being flatter, it will be much sharper, as you can see. The small gammas will kind of make the curve flat. Very sharp gammas, the very large gammas will kind of make the curve much sharper. Now, before I do theta, I should also say that delta and gamma are the ones that are probably hedged most of the time. The others are not really hedged most of the time because the ability to hedge them does not exist all the time. So what we say is that we will hedge them if and when an opportunity arises. So theta of a derivative portfolio is the rate of change in the value of with respect to passage of time. So theta of the call or put is change in option price with respect to time. Now, theta therefore stands for the option's position sensitivity to time decay. What does it mean? So long options have negative theta, meaning the time decay is actually eroding the time value portion of the option as the days pass. And therefore, time decay that hurts an option buyer and helps an option writer's position. Because as the long option, if you bought an option, and if you have not exercised, if the option is not exercised or exercisable, as the number of days elapse, the likelihood of the option exercise becomes lower, and therefore that kind of helps the option writer's position. So long options have negative theta, short options have positive theta. What is the formula? Again, the definition based on the same numbers, the same approaches. You see, again, the interesting thing is that all of them, they are essentially the function of the same 5 terms that we started off at option pricing. Spot, strike, time to maturity, interest rate, volatility. So essentially, they are on the same stuff that we are kind of looking at. Now, and this is for dividend. So this was for non-dividend paying stocks, and this is for dividend paying stocks. And you have an extra QT. So the formula essentially remains very similar. And all you can do is you can kind of take that in that framework and kind of calculate that. If I were to give you an example, this is an example for a 4-month put option in the stock in the same index that I had in the last case. Now T is 4 months, so 4 by 12, 0.3333. So what is the option of the option theta? This is a put option. So therefore, if I go back, realize that the put option is negative. So non-dividend paying stock, this is dividend paying stock, sorry. So therefore, I should use this expression. I get minus 18.15. Divide this by 365, which so this is the 18.15 is the every data is annualized, so this is annual. So therefore, I divide it by 365 to get it per calendar day, or you divide it by 252 to kind of get it per trading day, right? So that's how you kind of get that argument. Now, this is a relationship that theta, gamma, delta. This is a relationship that satisfies between the portfolio value, theta, delta, gamma, and theta. So look, we've done delta, gamma, and theta. So we can kind of use this to calculate the delta, so there is a relationship between theta, gamma, and So between theta, gamma, and delta. So theta is the change in time. Delta is with respect to change in spot. Gamma is the second derivative with respect to spot. And then S is essentially the spot price. So if you look at that, that essentially kind of gives you the change in portfolio value with the income, the interest in the portfolio value. R is the interest rate. So so for a small interval of time, R times pi, R times the portfolio value is exactly given by that expression. And obviously, therefore, if it is delta neutral portfolio, that term vanishes. So effectively, you have theta and gamma being equal to the change in the portfolio value. And if there is a dividend, then essentially the R gets replaced by R minus Q on this side for the delta for S, and then the rest of it kind of remain exactly the same. Vega is basically the rate of change of the value of the derivative with respect to change in the volatility. So Vega is delta pi over delta sigma. Options will, so this is basically the rate at which option price will change with respect to change in the volatility, the asset's volatility. What we saw earlier, remember, the options increase in value when the volatility increases. So therefore, volatility helps option buyers, hurts option writers. And hence Vega is therefore positive for long options and negative for short options. Also, Vega tends to be high for options that are close to being at the money and not otherwise. What is the formula? The formula for Vega for a non-dividend paying stock is given by that expression. Again, the same 5 terms in the option price is what I am using. Interestingly, whether it is a call or a put, the Vega is the same. So one can, this can be shown from the put call parity equation, because take the put call parity equation, differentiate both sides with respect to S, you will see you get del C equal to del P, because both cash and the value of the asset does not change with change in the volatility. Both cash and the asset does not change with respect to change in volatility, and hence delta C is equal to delta P, right? Sorry, del C del sigma is equal to del P del sigma. So the Vega of the call and Vega of the put becomes the same. And then therefore, the first one is when in a non-dividend paying scenario. The second one is on a continuous dividend paying scenario. Now, how do you manage the position? The most important thing is, and this is where the value where it becomes useful, or some of it becomes, kind of, you cannot do much with it, which is delta can be changed by taking a position in the underlying. So, I have a short position, I therefore buy the asset, I can take care of it. And I'll show you one quick example to do that. Whereas gamma and Vega can only be changed by taking a necessary position in an opposite option. I cannot do it otherwise. And that is something which will actually have to be looked into in that scenario. Finally, rho is the rate of change with respect to interest rate. And if you take with currency, there will be 2 rows, because with currency, there will be like a row with the foreign interest rate and row with the domestic interest rate, right? For non-dividend paying, but in general, if I take the simple case, for non-dividend paying stocks, the row of the call and the row of the put is given there, and you realize that this is negative sign out there. 2 negative signs are coming, the one outside, and the ND2 becomes N of minus D2. And the D2 definition is the same as that we had earlier. So rho stands for the option sensitivity to interest rates, which implies a positive rho means that higher the interest rates are helping the position, and a negative interest rate, negative rho means higher interest rates are hurting the position. Now, from a practical perspective, rho is the least important of all the Greeks as far as stocks are concerned. As far as stock options are kind of considered, right? Now, also we've got this positive or negative, and then on one hand we are saying they cannot be positive, they cannot be negative. Yet on the other hand, we get a plus or a minus sign. What does it mean? It basically means that on the assumption the underlying stock prices rise, time is moving forward, volatility and interest rates are increasing. Under that scenario, a Greek can be positive or negative depending on whether it is a long or short, whether you've got long or whether you've got short, and whether it's a call or a put. So if you've got long long, typically it is expected to be positive, or in some cases negative also. Sorry, in the theta case, and depending on whether it's a call or a put also. So if you look at this, if you take the four values, delta, gamma, vega, theta, and if you look at it for a long call, long put, short put, the sign of the Greeks should kind of replicate this thing. Delta should long for a delta, long call, sorry. For a long call, delta should be positive, gamma should be positive, vega should be positive, theta is negative. And similarly for the other one, short call, all is negative except for theta. For put, it is negative, positive, positive, negative, and short put is positive, negative, negative, positive. In that sense, delta, gamma, vega, theta. We really don't care about rho per se. The hedging, now to hedge, the basic argument is for delta neutrality, the delta of the portfolio has to be equal to 0. Delta of the portfolio is nothing but the sum of the individual deltas weighted about average. So therefore, that has to go to 0. For gamma, similarly for gamma neutrality and for vega neutrality, the same thing that happens. We also argue there's something called a self-financing portfolio. Why is the self-financing argument coming in? Because realize this is the Greek hedges are done by people who have written the options. Now to hedge, I need money. But I've already earned some money by selling or writing the options. So therefore, the additional amount of money that I will take is only the incremental amount that I need. And therefore, the value of that weighted value should actually go to 0. And that is what is called as a self-financing argument for self-financing. And I'll show you one example in a minute, in a second. Now, traders usually ensure that their portfolios are delta neutral at least once in a day. Whenever the opportunity arises using options, they will hedge, they will improve their gamma and vega. Also, finally, as the portfolio becomes larger, hedging becomes less expensive. Why? Because as the portfolio becomes larger and larger, the portfolio has inherent hedges within the portfolio gets created, and therefore automatically the risks come down, because if you benefit somewhere, you lose somewhere else, and so on. So automatically it gets adjusted, and if it gets adjusted, then that does not need to be additionally hedged. So that does not have any hedge cost, and therefore there is a automatic adjustment that kind of happens. Okay, let me show you the problem. Let me show you a few problems, and then let me show you the problems, and I'll go and show you another exercise. So I've sold 7-month European call options in Japanese yen. Spot exchange rate is 0.8 cents per yen. Exercise price is 0.81. Risk-free interest in the US is 8%. Risk-free interest rate in Japan is 5% per annum, and volatility is 15%. I need to calculate all the Greeks essentially. So what do? All I need to do is calculate all of this. What is my D1? What is my S0? 0.8. Strike 0.81. Interest rate R, which is interest rate in Japan, is 8%. So interest rate in US is 8%. We're doing it from US perspective. R is 8%. Japan, which is a foreign rate, is 5%. Volatility is 15%. And time is 7 months. So 7 by 12, that's how I get to 0.5833. Using this, I can calculate a D1 and my D2, and my ND1 and ND2. So therefore, my D1, and so now once I calculate my ND1, and I know that the delta of one call option is e to the power of minus RF ND1. I've calculated all the values, so I know what the delta of the call option is. What is ND? What is gamma? Gamma needs an N prime D1. Remember, gamma formula has an N prime D1. So what do? What is it? If ND1 is that N prime D1 is nothing but 1 by root 2 pi e to the power of minus D1 square by 2. D1 I have calculated. 2 pi I know. So essentially I can go and solve this equation, and I can find out N prime D1. Once I know N prime D1, I can plug that in, and I get a value of the gamma of one call option. Similarly, now I can plug in all of that, and I can calculate the vega, the theta, and the rho, right, for each one of them. So what is the interpretation? So when the spot price increases by a small amount, it's measured in cents, the value of the option to buy 1 yen increases by 0.525 times that amount. So essentially, if the spot price increases by 1 cent, the price of the option increases by 0.525 cents. Similarly, for gamma, when the price increases by 1 cent, the delta increases, not the price. So please understand the difference between gamma and delta. So when I say gamma changes, it is the price of the option that changes. When I say gamma changes, the change in gamma causes that change in delta. Gamma is a two-step process. Gamma causes change in delta. Delta causes change in the price of the underlying option. So that is the additional change that kind of happens in that process. And similarly, vega, theta, and rho can be kind of easily. I mean, we've calculated. So essentially, the change happens. If this change happens, that is the amount by which it goes up or goes down, whatever the case may be. If the negative side, it will go down. If it's a positive side, it will go up by that amount. Okay. This is another example. A bank has bank's position in options on the dollar euro exchange rate has delta of 30,000 and gamma of minus 80,000. How can these numbers be interpreted? Is the first question. And then the exchange rate is dollars per euro is 0.9. What position do you take to make your position delta neutral? After a short position of time, let's say the exchange rate has moved from 0.90 to 0.93. What will be the new delta and how much more trade is necessary to keep the position delta neutral? And let's start with the assumption that originally it was a delta neutral position. If that was the case, has the bank made money or lost money from this movement? So let's start with the first one. So what happens? The delta of 80,000, 30,000 and gamma of minus 80,000. So delta, and what does he have? He has a position in options. So the first thing, what happens when the euro value increases by 1 cent, the value of the bank's position increases by 1 cent into 30,000, which is $300. Similarly, for the gamma, when the value of euro increases by 1 cent, the delta of the portfolio decreases by $800. So it's not the price does not, the value of the bank's position does not decrease, delta decreases by $800. So therefore, to kind of balance the delta neutrality, so to get delta neutrality, what should you do? You should short delta because if it goes up by 800, your position goes up by 30,000 delta of 30,000, which is 300. So therefore, if you want to make it delta neutral, you should kind of have something that will go the other way around. So you short the delta. So you short 30,000. You short 30,000 euros because that is how you will get the 300. Now, when the delta moves, when the exchange rate moves up to 0.93, you expect the delta to decrease from 0.9. How much? 0.93 into 0.9, so 3 cents. 0.03 cents into 80,000 delta decrease, which is 22,400. So that, and then it was originally, the delta was originally 30,000. Now it has gone down by 2,400. So now it becomes 27,600. To maintain the delta neutrality, it is therefore necessary for the bank to unwind the short position in 2,400 euros so that a net position of 27,600 has been shorted. So that is what has to be mapped onto this side to ensure that you have a delta neutrality. So as the delta neutral, and so when you have a slightly negative gamma, the loss is experienced when there is a large movement. So when the portfolio is delta neutral and there's a negative gamma, a loss is experienced when the large movement in the underlying asset price. So basically, we will then expect that the bank to have lost money because in both scenarios, you see the bank is kind of losing money in most cases. Finally, this is a problem with the portfolio. I have a call. What is the position and how? So there is one call which I have shorted 1,000 calls, 500 calls, 2,000 puts, and 500 calls again. And these are 4 different options on the same underlying, each having different deltas, gammas, vegas. Now you have a traded option available with delta. A new option is available with a delta of 0.6, gamma of 1.5, and a vega of 0.8. How will you make, so what kind of position should you take to make it delta gamma neutral by taking a position in the in sterling? I mean, it's on the sterlings, right? And similarly, both Vega neutral and delta neutral if you want to. So look at the first one. So what do? I first find out the delta of the portfolio. This is my existing position. What is the delta of the portfolio? So I know minus 1000 into 0.5, minus 500 into 0.8, minus 2000 into minus 0.4, minus 500 into 0.7, and add them up. So when I add them up, that gives me a delta of minus 450. Similarly, I can calculate the gamma of the portfolio, minus 2.2 into minus 1000, and so on and so forth, and Vega of the portfolio, 1.8 into minus 1000, and so on. And that is what I have done. So my gamma of the portfolio is minus 6000. So what I get, delta is minus 450, gamma is minus 6000, Vega is minus 4000. That is in the current portfolio. Now I need to get my part A's. I have this option and I have sterling and I want to make it delta and gamma neutral. So what do? Remember my delta is minus 6000 and the new option is a gamma of, gamma is minus 6000 and the new option is a gamma of 1.5. So therefore, if I'm negative out there, so I need to be positive. So I need to buy, so I need to be positive gamma. So I take a long position. And how many options do I take? 4000 because my gamma is 1.5. So 4000 into 1.5 is 6000 because that will ensure that I give a gamma neutral position. But having bought 4000 options, what will happen to delta of the portfolio? I have 4000 options and delta is 0.6. So 4000 into 0.6 minus, which is 2400 minus, I have my original delta of minus 450. So it has now gone to 1950. So therefore, in addition to kind of buying 4000 traded options, you would need to create a short position in 1950 sterling so that it is both gamma and delta neutral because you have a positive gamma of 1950. So if you have a short position of gamma in a short position in sterling of 1950, that will adjust, that will cancel each other out in the event of a movement, and the delta is neutralized, so you get a delta gamma neutral position. And for the last part, finally for the last part, what happens? You have a long position in 5000 traded options, will give a Vega or neutral position. Since Vega has a 0.8, so basically if I take 4000, my Vega was 4000, I needed to 4000, so I need therefore to trade at 5000 and 0.8. But there was minus 4000, so I have to go long, so I take 4000. But the moment I take 4000 options, what happens? The whole portfolio, including the traded options, becomes 5000 into 0.6 minus the original 450, so that becomes 2550. So therefore, in addition to 5000 traded options, I would need a short position in 2550 sterling to ensure that the portfolio is both Vega and delta neutral. That is how I can calculate. That is how I would be able to calculate this to be both Vega and delta neutral. Okay, I just want to show you one other example. If I can pull this up, the Excel sheet. Yeah. I don't know if you can see this. So what I've done out here is I have kind of said your short position in 10 contracts, call contracts. One contract is 100 shares. So you have to, yes, please go ahead. You have a question. You raised a hand. Somebody just raised a hand. Please go ahead. Oh, okay. So, fine. Well, I'll just quickly show you this and I'll just make it full screen and quickly show you this. Same thing that I did earlier. So what I've done is I have my position is 10 short, 10 call contracts. One contract is 100 shares. So 10 call contracts, or in all I have to short 1000 shares. 1000 10 call contracts, one contract is 1100. So basically 1000 is the total number. If you look at it, I have given you all the information. Right? Now I have two options that I can kind of, so I have option 1 and I have option 2. And there is a reason for that. And I have calculated using the data, all the data is there. You can see all the data: strike, maturity, volatility, interest rate. I have the time to maturity also somewhere. I have the strike price, spot, strike. I have the maturity in days. Yeah, my spot is so I have where is the spot? Yeah, current spot strike price is 55, 50. I have forgotten to put the spot. The spot is also 50. Right? The spot is also kind of 50. The spot is also taken to be 50. So what is there? The strike price is there, spot, everything is there. So I can calculate the price of the option. I can calculate the, so yeah, the price of the underlying stock is 50. You can look at it out here. It is kind of stated out here. And therefore I can calculate the delta of the stock, and all of the gamma and all will be zeros. But I can calculate for the two options that I have, I can calculate all of it. Now what I'm saying is I want to hedge this. So I've calculated my D1, D2, ND1, ND2, and all of that can be computed. So using that, I have calculated my delta. Delta is nothing but ND1, and so on. So I've done all of that in each of the cases. So this was the original option that I want to hedge. These are the options available in the market. So I want to buy now. To hedge, I need to buy options. I need to buy options, and I need to buy. And I need to hold on to share. I need to buy shares, and for that I would need cash. If I only wanted delta neutrality, what would happen? I mean, what is my delta of the call? 0.567, and I've shorted, so it will be minus. So 10 contracts. So look at this expression: 10 contracts into 100. Each contract is 100 into the delta plus number of shares I want to buy. Delta of shares is always 1. So that has to equate to 0. So therefore, I need to buy 561.2 shares today to be delta neutral, or 561 shares. Right? So because that is a negative sign, negative. So, so that is what my number of shares that I would need to kind of get. If I want delta and gamma neutrality, what will I do? I'm buying N1 shares. I'm buying N2 options. First option. So I will have that for delta neutrality. I will have delta of the shares is given. For gamma neutrality, I will have the other one, but realize that gamma of stock is 0. So from that, if I solve, I will get N2 is 1092 and N1 is 238. So what do? I need 238 shares of the underlying stock, and I buy 1092 call options, which is basically approximately 11 contracts. Similarly, if I want to do delta gamma vega neutrality, I now use the second option to do that. So I have the first one for delta neutrality equation, the second one for the gamma neutrality, and the third one for the delta neutrality. Now I can solve for this because N2 and N3 will be simultaneous equations, so I can solve for it. And then go back to the first equation and solve for N1. You'll end up getting N1 is, and therefore you get N1 to be 381.9, so 382 shares. You buy 382 shares as underlying. You buy 547 options of the first type and 161. Sorry, I don't know why that's a typo. It should be 161. 161 options of the second type, 2 contracts. So 547, which means approximately 5 contracts. 164, which is each contract is 100 shares, so 2 contracts to kind of get the delta vega neutrality also. So basically, you can calculate your delta gamma. You can kind of therefore show the delta gamma vega neutrality with a self-financing argument. So I've done it separately. The first one is delta neutrality with self-financing. Second one is delta and gamma neutrality with self-financing, and delta gamma vega neutrality with self-financing. One last point. I can do delta neutrality without doing gamma neutrality. but I cannot do gamma neutrality without doing delta neutrality. So I have to get to gamma neutrality. I need to do delta neutrality. To get to Vega neutrality, I do not need gamma. I could have simply done delta and Vega, or I could have done delta and gamma, or delta gamma Vega. But I cannot do gamma or Vega by itself. To do gamma or Vega neutrality, I will always have to adjust for the delta neutrality part of it. But delta can stay on its own, and that is the advantage that I kind of get in that process. Okay. Okay, so that's all that I can cover today. I'm already out at over time, so I will stop with this today. We will start tomorrow. So tomorrow I just want to show you the blacks option, and then I want to show you swaps. Uh, so are you guys ready with your presentations for tomorrow? Hmm. No, I don't have any particular order. We have 8 groups. We can just go 1, 2, 3, 4 in that order. So I don't have any particular specific order. Okay. Do you want to have an order? If you guys want to have an order, you can create an order. I don't have a problem. Okay, but please make sure that your presentation is no more than 10 minutes. We preferably 8 minutes, but no more than 10 minutes. Okay, so that we can finish all the presentations. Okay, I'll stop with this. We'll stop with this, and I'll see you tomorrow.